Okay, good. So this is number 7 out of 8 in the mini course on optimal transport and high-dimensional probability. And so far, if we're honest with ourselves, we did mostly optimal transport. There wasn't a lot of high-dimensional probability. But hopefully this lecture will fix it. And as you may recall, in the previous lecture, we explained how we can use the autocalculus on the Wasserstein space in order to derive functional inequalities such as log-Sobolev inequality, which here I remind you what it is. We say that mu, a probability measure, satisfies log-Sobolev inequality with constant c if the relative entropy between rho and mu is upper bounded by this constant c times the relative Fisher information, and this should hold for all rho. And we also had a transport inequality like the W2 inequality, and they all followed from this machinery of gradient flows on the Wasserstein space, and we've also seen how to use them in order to show convergence, the equilibrium. And in this lecture, the idea would be to use those functional inequalities to prove results about probability measure, and the type of result that we'll show will be concentration of measure, which would mean that random variables concentrate around their mean. And a good reference for it is a chapter 4 from the lecture notes of Ramon van Handel, probability in high dimensions. So because we're getting towards the end of the mini course, I won't prove all the thing, and I will just sketch things quickly, and I'll try to state more things rather than prove them just because we're running out of time. Okay, so let's start with a short intro. So if we take x to be distributed according to a standard Gaussian, and we take f to be linear, so we should think, of course, of maybe f of x is equal just to the average, let's say. Then we know that if we look at the deviation of f from its mean, of course the mean here is 0, but I'm writing it just to emphasize the point. It will be upper bounded approximately by, it will have Gaussian tails for some sigma. So really all I'm using here is the tail of the Gaussian. I'm writing it in this particular way, which will be clear in a moment. But the point is, for us, a statement like that is the statement that f of x concentrate. Because the idea is that if I look at how much it deviates from a mean by an amount t, it decreases exponentially fast in t. Of course, you can put absolute value and things like that, but I want to make it simple, so I'll just have one-sided bound. So for this particular f, and for mu being a Gaussian, this just follows from the properties of the Gaussian. So the type of question that we want to answer in these lectures are two questions. So first of all, what if f is not linear? And the second question is, what if mu is not Gaussian? Do we still have setting where we get this type of concentration for different measures of mu and for different functions? Okay. So the first results would be understanding how the log-Sobolev inequality is tied to functional inequalities. So here we will tie the LSI to sub-Gaussianity. So sub-Gaussianity is a natural generalization of what does it mean for a random variable to be Gaussian. It just means that the tails behave like Gaussian tails, but let me use a different definition. So there are equivalent definitions for what does it mean to be sub-Gaussian. We'll use one which will work very well with the log-Sobolev inequality. So here's the definition. So let mu be probability measure. On our n. And let's take a function And I'll take the function to be centered with respect to mu, just to simplify things. So we say that f of x, where x is sampled according to mu, is sigma squared sub-Gaussian if we can bound its log moment generating function. So here we're taking the log, and we're taking the exponential of e to the t of x, and we integrating with respect to mu. This should be upper bounded by sigma squared over 2 t squared for every t, and sigma is called variance proxy. So this is the definition about what does it mean for f of x to be sigma squared sub-Gaussian. So a good exercise check the case where mu is Gaussian and f is linear. Okay, so why is this a good definition? Well, it's a good definition because of the following simple lemma that shows us how to use the fact that the log moment generating function is upper bounded by this quadratic, how to use that to get tails. So this just follows from Markov's inequality, but let's just write it down. Any questions? So let's suppose that f of x, where x is sampled from u, is sigma squared sub-Gaussian. So I'm assuming implicitly that the mean is 0. So the deviation from the mean, so the probability that f of x is greater than some z, mu. So x is sampled according to mu, is upper bounded by this Gaussian tail. Okay, you can do lower tail as well, but... So the proof is simple. It just follows from Markov's inequality. So we want to understand the deviation that f of x is greater than z when x is sampled according to mu. So we exponentiate on both sides, or we fix any t, so fix t. So we exponentiate on both sides. Now we use Markov's inequality. And now we use the sub-Gaussian assumption. The sub-Gaussian assumption said that this log moment generating function was bounded by t squared. So if we just exponentiate, we get sigma squared t squared minus tz. And now we just optimize in t to get the bound. Yes? You're asking here? Z should be, what do you mean by over? Oh, so let me just write it just in case it's, what I mean to write is that better? You mean the 2 over sigma squared? That's possible. Because when I do the optimization, you're saying it's going to flip. I think you're right. Okay, so we will leave it like that. Yes. And okay, yeah, it should be because that's just a variance. So, yeah. Thank you. Yeah. Okay, good. So the logic so far was if you know that you're sub-Gaussian, then you get the behavior of a Gaussian, which is decay like with sub-Gaussian, with Gaussian tails. Okay, so that's why this definition is a good definition. It captures what does it mean to be similar to a Gaussian. So in that sense, we're trying to go beyond this result here where we assume that mu was a Gaussian. Of course, now we have to find a way of actually proving that f of x is sub-Gaussian for a given mu. So we need some technique to do that. So this is really the connection, the functional inequality. So I'm going to credit it to Herbst. If someone wants to correct me, please feel free to do so. But I think he should be credited for it. So here's the result. So let's suppose that mu satisfies a C LSI. So it satisfies the Sobolev inequality with constant C. Then, for every f which is 1 Lipschitz, so if it's differentiable, that would mean that the gradient is upper bounded by 1 in norm. We have that f of x, where x again is sampled according to mu, is, and the constant is going to be, I think it's 1 over C sub-Gaussian. We will see whether the constant is in C. Okay? So that's a connection to functional inequalities because the statement is that, so there are, just notice here we asked, how do we go beyond the setting where f is linear and mu is a Gaussian? So this is one answer. We went beyond the Gaussian setting by saying that mu satisfies Sobolev inequality. Okay, we'll see exactly what that means, but at least it's something, so we know the Gaussian satisfies Sobolev inequalities, but as we've seen in the previous lecture, if the distribution is strongly log concave, it also satisfies Sobolev inequalities. So we already are outside the Gaussian setting, and we're also outside the linear setting because we're allowing the function to be 1 Lipschitz. So we make some assumption about f, but it doesn't have to be linear. Okay. So how do we prove that? So we recall the definition here. That's a definition of what it means to be C sub-Gaussian. So somehow we need to get this inequality combining the fact that mu satisfies Sobolev and the fact that f is 1 Lipschitz. Somehow these two facts should come together to give us what we want. So I'll just sketch. So we fix t. And we take d rho, we define it to be e to the tf d mu. And then we have to normalize to make sure it's a probability measure. This is called the tilted measure. And now we just write down a computation. So here I'm writing t over e to the tf d mu. So it's t over the normalization constant. And then we have f times etf d mu minus log etf d mu. So here I'm just writing an identity, so you can check. Sorry, I realize that I should fix the notation. So here I meant the KL divergence, just to be consistent with the notation from previous lecture. So here we have KL divergence between rho and mu. This is just, you can just check. But by assumption, mu satisfies Sobolev inequality with constant C. So we upper bounded by the Fisher information. And now we just recall the definition of the Fisher information. So we get C t squared, the integral of gradient of f squared d rho. But now we use the fact that f is 1 Lipschitz. So this term here is upper bounded by 1. Because point-wise, this is bounded by 1, and then we integrate against rho. So the whole thing is upper bounded by ct squared. So we're going to call this bound star. So the conclusion is that this expression is upper bounded by ct squared. So now let's see why is that useful. So again, it will be just like last lecture, it will be a differential inequality that is hiding here in the proof. Because now we will define zt to be the log moment generating function, ETF d mu, and then we can check that the derivative is equal to f with respect to t, f df d mu, and then over the normalization. But now this is starting to look kind of similar to the type of term that we have here. And then you can check that star implies that t times z prime of t plus z of t is upper bounded by ct squared. And from here you can conclude that zt is upper bounded by ct squared, but zt is nothing but the log moment generating function, and this is exactly the definition of what it means to be sub-Gaussian with constant c. So the idea of this proof, again, just to summarize, you want to show that something is sub-Gaussian, so you have to get a bound of this form. So we form this function z of t, which is the type of log moment generating function that appears here, and then you derive a differential inequality for it in order to get the appropriate bound. Now, how do you derive the differential inequality? You simply write down the computation when you differentiate it in t, and then you realize that the type of terms that show up are terms like relative entropy. So if you have log Sobolev inequality, you get a Fisher information out of it. Okay, how does the Fisher information term helps you? That's where you use the one Lipschitz assumption to get just t squared term. Here?
Would there be a minus?
Maybe there's a minus. That's possible. Minus here, maybe?
Minus ET.
Minus ET. Okay. Yes, because there is a minus here. Okay. So if there aren't any questions, I'll move to the next section where we will make a connection between a transportation inequality and concentration of measure. So this was just a connection between log Sobolev inequality. So here we're going to look at the relation between W1 inequality and sub-Gaussianity. And I remind you that the W1 distance between rho and mu is written at the infimum over all coupling between the two measures of the distance function. So we do not square the distance functions. That's why it's W1 and not W2. Okay. So in the previous result here in the theorem of Herbst, what we saw was that if you satisfy log Sobolev inequality, then you're sub-Gaussian. So it was a sufficient condition. It's not a necessary condition. So the question is, do you have a necessary and sufficient condition to characterize sub-Gaussianity, but in terms of functional inequalities? So this is the content of the next theorem. This is due to Bobkov and Götze. So I'll say the following are equivalent. Okay. So the first statement is that f of x, when x is sampled from u, is sigma squared sub-Gaussian for all f which is 1 Lipschitz, which was the type of statement that we had there. And the second statement is that we have a W1 inequality. So the W1 distance between rho and mu is upper bounded by the square root of 2 sigma squared and then the KL divergence between rho and mu. And the sigma squared that appears, of course, here in the functional inequality is the same sigma squared that appeared in the definition of sub-Gaussianity. So now we have a characterization of sub-Gaussianity for one Lipschitz function in terms of a functional inequality for the measure mu. So let's see how we can prove the theorem. So the proof of the theorem requires a certain lemma, which is kind of fundamental in its own right. So I want to write it down. This is called the Gibbs variational principle. So let's start with this lemma, which is Gibbs variational principle. So the point is, for sub-Gaussianity, we define it in terms of bound on the log moment generating function. Here in the functional inequality, we have the Wasserstein distance and we have entropy. So not so clear how it's related to log moment generating function. The point of the lemma would be to actually relate KL divergence and the log moment generating function, which is exactly the statement in the Gibbs variational principle. So the statement is that log of, this is for any function g, you can write as a supremum over rho of the integral of g with respect to rho minus the KL of rho with respect to mu. So I won't do all the computation required to prove the lemma, but I'll just start them and you can continue them on your own. So to prove the lemma, you define this tilted measure, d mu tilde, as Eg d mu, and then you just normalize. This is for all g. And then you, just by the following computation, you write that log of Eg d mu minus the KL divergence between rho and mu tilde. You do a bunch of manipulation, but they're all identities. And then at the end, you get the integral of g d rho minus the KL rho and mu. And now you take sup over rho. Okay. So we can take this lemma as a given for now. And try to prove the theorem. So we need to show that sub-Gaussianity is equivalent to this functional inequality. So one, which is the sub-Gaussianity statement, is equivalent to the following statement. So if I take supremum over t, then I take the supremum over f, which is one Lipschitz, and then I take the supremum over rho of the expression t multiplied f d rho minus f d mu minus the KL between rho and mu minus sigma squared over 2t squared. This whole expression should be smaller than 0. So why is 1 equivalent to the statement? So what are we using here? So the first supremum here that we're using over rho, that just expresses the log moment generating function according to the Gibbs variational principle. The second supremum, which is over all f, which is 1 Lipschitz, we're just expressing the fact that in condition 1, the condition 1 had to hold for all Lipschitz. And the third supremum, which with respect to t, expresses the fact that in condition 1, it had to hold for all t. Okay? But if whenever you see 3 supremums appearing next to each other, you feel just like a compulsion. You have to start switching them. You must do it. So when you start switching them, so let's take out the supremum from rho outside, and then do the supremum of F1 Lipschitz, and then we do the supremum of T over the whole thing, what you find out that if you just stare at it as a function of T, this is quadratic in T. So you can actually solve it. You just fix rho, you fix F, and you just solve it in T. So you solve for T, and you get that the optimal T is equal to the integral of F d rho minus F d mu over sigma squared. You plug it in, and then you get the supremum over F1 Lipschitz. So I'm not taking the supremum yet over rho, just the supremum over F1 Lipschitz of 1, 2 sigma squared F d rho minus F d mu squared minus the KL between rho and mu. Okay, so this is just what happened when you take the supremum over F, but not over rho. But I claim that now we're done. So why is this essentially just a W1 inequality? How can we get from here to the W1 inequality? So one term is good. We have the KL. That's good. That also appears in the W1 inequality. What does this have to do with W1? Exactly. So this is just duality. So as we talked about duality for the characterization of WP in general, and not just a characterization for W1 in terms of one Lipschitz function, which we've used in previous lectures. So this one is just equal to W1, and therefore, and because you have a sup over all rho, it holds for all rhos, and not prove the theorem. Okay, so it's quite nice. We see how the various tools that we use throughout the mini course kind of all come together: differential inequalities, functional inequalities, duality. Okay, so maybe I'll just write use duality for W1. Questions? Yes.
Can you work with storm exponential?
I think you will have just different type of functional inequalities that would. Yeah, or maybe just as natural, but then you will have to. So a lot of these functional inequalities do generalize.
There you would get just a different power.
Right, right. Yeah, yeah. So in a lot of these functional inequalities, you can replace things like. So for example, in the KL, you had. The entropy appearing, so you have the function log, but then this function log can be replaced by another function, like which is convex, like phi. And so,
it's not quadratic, then maybe when you get the optimizer,
I'm not sure whether you can get a sharp result, but I think at least part of the theory generalizes, I think, and just different type of functional inequalities. But I should say, so for some of these more general or functional inequalities, the proofs are actually identical to that we've seen so far. Because really, we just, under the hood, we just use the fact that in KL we have some convexity, so you can replace it by other convex functions. Okay. So, so far, we used two. We saw two examples for functional inequalities and their connection to concentration. One was showing how LSI, Sobolev inequality, implies that, meaning if the measure is satisfied Sobolev inequality, then one Lipschitz functions applied to samples from these measures are sub-Gaussian, and the other one was actually a characterization in terms of W1, but all these statements were for a fixed measure on a fixed space. We just said, if you take a measure mu, you sample from it an x, and then you apply an f to it, when does it concentrate? So that was just for a fixed space. But when we care about, when we say probability in high dimensions, one aspect of it is understanding what happened as I have more and more sample and the dimension goes to infinity. So in this next section, I want to explain that. And it will become more clear what I mean by that. So we'll call this tensorization and WP inequalities. So from now on, I'll mostly state results rather than prove them. So here's the theorem of Marton. So we will take mu I to be probability measures on metric spaces xi with metric di. And each one of them satisfies a W1 inequality. So by that we mean that if we look at W1, rho I, W1 between rho I and mu I should be upper bounded by 2 sigma squared, and then the KL between rho I and mu I for every I. Okay, so this is the assumption. So we're assuming that each of these measures satisfy the W1 inequality. We're also assuming that we have the same constant. We just can take the worst constant. Okay, so that's the assumption. And then the conclusion is that if we look at W1 between rho and the product measure of mu1 to mu_n, it will also, so meaning, in other words, the product measure mu1, mu_n would also satisfy a W1 inequality. And actually with the same constant, which does not depend on the dimension. This is for every row on this probability space x1 to xn. Okay, so this is where the point where probability in high dimension comes in. Each of the components satisfied this functional inequality, which give concentration with some constant. And then when we took the product measure, we still satisfy the same functional inequality, and the constant remained the same and does not blow up in the dimension. So actually, the statement doesn't quite make sense as I wrote it. I'm missing one thing here, which I didn't really define, and therefore the whole thing is nonsensical. Yeah, exactly. So, I mean, I wrote W1, but W1 with respect to what metric? I just defined metrics on each of the components. I didn't define the metric here. This is crucial. So let's write out what is the metric that this holds true for. So where W1 is with respect to the metric D, which we define dxi to be the sum from 1 to n, ci, di, xi, yi, for all c1 to cn, such that the sum of the square is equal to 1. Okay, so the first thing to note is that it's not like there's a canonical way of taking metrics which are defined in each component and building a metric from them on the product space. There are multiple ways of doing it, and doing it in different ways would give you different results. Here, we're taking this particular metric. So, but already with this metric, we can prove a pretty interesting result, such as the following. Yeah.
So differentiation
So yes, but it's not so much about the CI. Yes. This is the less interesting part.
So what you mean is that for all choices of CI, then the inequality therefore.
Yes. But when I was talking about choosing different types of D, I didn't mean choosing different types of C. That you can do that. For example, what we will see later, we could. So I'll write just not to confuse and not. So we're not doing dxy is equal to the sum from 1 to n of di xi yi squared, and then taking the square root. We could have also defined this metric. And this metric, so, okay, we're jumping a little bit ahead, but if we chose this metric, then we would be able to recover the type of sub-Gaussian concentration that we saw before, because if you think about it, this is just a Euclidean metric. But if you use this metric, you would not be able to recover the Gaussian results. So this result at the moment is not strong enough to recover some of the things that we've seen before, but I want to show you how it is strong enough to get already interesting results. Okay, so I'll come back to this point. Yeah. Here that for every CI with this normalization, for every CI with this normalization, you take W1 with respect to that distance, and this is true. That's the claim. No, rho can be anything. Okay, good. Yeah, thank you for explaining, for asking. So here we had the mui's and then we formed the product. The rho should be any rho on the product space. For all rho on the product space. Because that's how this function inequality is defined. Whatever space you work on, the rho should be defined in that space and it should be whatever rho. Exactly. Exactly. So here the assumption is that for every rho I on the space xi, sorry, yeah, I did not write it. Thank you. So maybe we should replace for all rho I and then for all I. So then the assumption is for all rho I, and therefore you get it for all rho. Okay, so let's look at one example where we can use Marton right away to already get an interesting result. Okay, so yeah, maybe I was just about to say that sentence, and I decided not to say it, so now you're forcing me to say it, which is there are multiple proofs of the are you asking about this inequality?
No, but there you have a choice in the CI. By doing the couplings, that choice is...
I'm sorry, if you do what with the...
So if I define W1 with the couplings, like I do with all the couplings of the rho and the tensor...
But with respect to what metric? So W1 is always defined with respect to some metric on the product space that you have to define the... Okay. But I was going to say that the next result that I'm going to show has multiple proofs, and here I'm just showing you one, but... Good, yeah, so I don't have the time to show you the theorem, but okay, because you've asked, I'll just say it in words. How do you go about proving a theorem like that? You kind of proceed by induction, and you build your so, whenever you work with W1, you need to use some optimal coupling, because that's the definition of W1. And what you do is you build your optimal coupling from you condition on one coordinate, you use some optimal coupling there, and then you proceed by using the optimal coupling from the one coordinate to move to the next one, and so on. Yeah, so the proof is a little, you have to be careful on how you do it, but the main idea is really to proceed by induction. Okay. So let me do the example, which is called make the Armid's inequality. I don't know, in this field of inequality, whenever people say Chernoff, Hofning, I never know what they mean. I just write down the inequality. I don't know what you mean with. So this one, I'll just write down the inequality because for different people, this means different things. So what is the metric that we're going to work on? Here's what's nice about this example. We're really going to start with the most basic metric. So I'll just take the metric which is the trivial one, as sometimes it's called, which is 1 if xi is different than yi and 0 otherwise. Okay, that's a legitimate metric. I'm allowed to use that. So Pinsker's inequality tells you that actually every measure mu I would satisfy a W1 inequality with constant, I don't know, the sigma squared comes out to be a quarter or something. So the point is this is true for all rho I. Okay, fine, that's just the definition, but the point is for all mu I. So it doesn't matter what mu I is, you would satisfy W1 inequality. So if each of these components satisfy W1 inequality, then we can apply the theorem and get something out of it. The question is, what do we get? So, okay, maybe continue here. So Marton is telling us that for every row, if we look at W1 between rho and the product measure, it will be upper bounded by the same constant, and then the KL between rho and the product measure, you have square root. And where, of course, the W1 is with respect to the metric, let's call it dCxy, which is sum from 1 to n of Ci1 xi different than yi. And again, we need the normalization. Ci squared is equal to 1. Okay. Good. But now, so now we know that this product measure satisfies W1 inequality with respect to this particular metric. What is the next result that we can use that we saw today? Yeah, we can use Bobkov-Götze. So now we use, because remember Bobkov-Götze told us, what they told us that we have an equivalence between satisfying a W1 inequality and having sub-Gaussianity for one Lipschitz function. One Lipschitz with respect to what metric? One Lipschitz with respect to this metric. So they would tell us that f of x, if we sample x from this product measure, is 1/4, I think that's the right constant, but that's not crucial. Sub-Gaussian for all f, which is 1 Lipschitz, but 1 Lipschitz with respect to this metric dc. Okay, so now we just need to put together all these things and parse them in order to get a result which looks easier to deal with. So let's define this discrete derivative dIfx as, these are just derivatives that when we fix all the other variables and just change the variable at the position I, and we change it in the worst way. So we take the sup over z, and then we have f of x1, xi minus 1, and then we put z where xi should have been, and then we keep the rest the same, and then we subtract the infimum over z of the same quantity. So this is like the evil derivative, basically. So let's call these things dIf. So then if you just work out, this is really just an exercise in checking that we've actually understood what all these things mean. What you will find is that the corollary of all of it is that if x1, xn are independent, so they're not even IID, just independent, then f of x1, xn is 1/4 sum over I from 1 to n of the L infinity norm of DIF squared sub-Gaussian. Okay? So the point is, we only assume that the random variables are independent. We're not even assuming that they're IID. We're not making any assumption about the function. F can be anything. And the statement is that it's always sub-Gaussian with this particular constant. Now, of course, in application, it's very much possible that this constant is going to be infinity, depending on your function f, and therefore it's useless. On the other hand, in other applications, it could be very useful. So this corollary, we got it from a combination of Marton, Bobkov-Götze, applied to the particular metric, which is the trivial metric. As you can imagine, one can repeat the story for different types of metrics. Okay, so I'm starting to run out of time. Okay. So as I mentioned before, this result of Marton is not strong enough to get the sub-Gaussian result for meaning with respect to the Euclidean norm, because given the metrics on each of the component of the space, the way we formed the metric on the product space was just by summing up some combination of the metrics on each of the component. But really what we want to do is we want to get a Euclidean component for which we would need a metric like that. But however, there is it just follows from Marton that, so remember in Marton the assumption was that each of the components satisfy W1, and then we get W1 for the product measure. There's actually a version where you say each of the components satisfies W2, and then the conclusion is that the product measure also satisfies W2. And then you will, and with respect to this particular metric. So basically, as the time goes on and the lecture is about to end, I will become less and less coherent because I'm trying to squeeze as much information as I can. Okay. Let me try to think what would be a good idea to do in the last 5 minutes. Okay, so there are some other results like that. There are also some very interesting results about characterization of precisely the sub-Gaussian properties due to Gauss's law. But I think it will be a little difficult to cover it in the next 5 minutes. Also, it's kind of delicate to understand the connection between all these various functional inequalities. So I would highly recommend this chapter 4 in the lecture notes. It's really beautifully written and explained very well. So if you want to know more about it, read there. Maybe I'll just try to end by giving a bit of a different perspective, which is more geometric in nature. So another approach towards concentration of measure is through something called isoperimetric inequalities. So isoperimetric inequalities are statements. So the most classical one is if you look at all shapes that have the same volume, which one has the smallest surface area? The answer is a ball. This is an example of isoperimetric inequalities. We'll see it done in a bit of a different way. But it turned out that from these inequalities, you can actually get concentration of measure. So that seems like another route toward concentration, which starts from geometry. But what I'm hoping to show in the remaining 2 minutes, so it's not going to happen, is that there's actually a way for going from functional inequalities to isoperimetric inequalities to concentration. Okay. So to say that mu, to say that it's okay, so we'll say that so mu satisfies a parametric inequality just means that if we take a set A, which has a lot of mass, so the probability is greater than a half, and then you expand it a little bit, that's what A epsilon means, you expand it a little bit by epsilon, then you capture almost all of the mass. Meaning it's almost 1 except for some exponentially small part. So this is like very highly non-trivial, right? You started with a set, which all you knew about, the only thing you knew was that it has measure more than a half. Then you say if you expand it by epsilon, it's almost 1. because the rest is just exponentially small. So this is what it means to satisfy isoperimetric inequality. So turned out that this is equivalent to sub-Gaussianity. Okay, so the two things are equivalent. That's another approach toward concentration. And then to finish, the W1 inequality actually implies isoperimetry. And maybe just to say a little bit about it, what's the connection is, if you want to understand the connection, the distance, okay. I think it's, I'm running out of time, so let me just stop here and just say that there's another perspective on. Okay. Okay. So, I mean, I don't think I'll have time to prove any of it, but just to explain what kind of, for example, in W1 inequality, how do you get to isoperimetry? What type of measures would you use? So, for example, what you would do here, you would take A and A epsilon, and you want to show, you take, let's say, A epsilon, which is the expansion of A by epsilon, and you would take its complement, and then you would take your measure mu, for which you want to show that you have isoperimetric inequality, and you will restrict it to these two sets. Then you will apply your W1 inequality, and that's how you will show that you have isoperimetric inequality. If you want to show that these two things are equivalent, so to go from one to the other, you will either choose a particular set A such that you get sub-Gaussianity, or in the definition of sub-Gaussianity, you will choose a particular function f to get this. So for example, the function f that you would choose here would just be the distance function and things like that. But yeah, I think I don't have the time to actually show you what's going on in details, but I'm happy to talk about it offline. So maybe let me just stop here.